After completing general chemistry and moving into the organic sequence, the first actual reaction discussed is usually acids and bases. While this topic uses the same ideas and language as general chemistry, the level of understanding needs to improve so that you are able to use acid-base chemistry as the foundation of many other reactions throughout the organic chemistry courses. An in-depth discussion of how and why bonds are formed and broken, along with a sound knowledge of pKa values, gives a platform on which to build. We begin this discussion by reviewing the early ideas of what constitutes an acid and what constitutes a base. The early Bronsted-Lowry definition tells us that acids are proton donors and bases are proton acceptors. These molecules react to give the conjugate acid and conjugate base. For most of the organic sequence, you will notice that acids typically have the proton attached to a more electronegative element, which was the case in general chemistry with acids like hydrochloric, sulfuric, and nitric. Many of the acids that you've come across before are also used as reagents in organic chemistry. Hydrochloric, sulfuric, hydrobromic, nitric, and hydroiodic acids are all still exceptionally powerful and will be capable of protonating even weak bases. In each case, the acidic proton is bonded to a more electronegative element, which makes that proton-electron poor. That proton will therefore be able to attract electron-rich bases. Likewise, many of the bases used in general chemistry are also employed in organic reactions. Sodium hydroxide and sodium carbonate are simple examples, and can be compared with specialized bases used in organic chemistry, such as sodium amide and methyl lithium. Some common features appear in the basic atoms, while the metal ions are usually spectator ions and play no role in the acid-base reaction. The anions involved feature an excess of electron density that make them basic. These electron-rich anions will be attracted to electron-poor protons. Beginning with an example from general chemistry, we know that mixing sodium hydroxide and sulfuric acid leads to water as the conjugate acid and sodium hydrogen sulfate as the conjugate base. We are interested in how and why that happened. It should be obvious that the electron-rich oxygen in hydroxide acts as the base and is attracted to the electron-poor proton on sulfuric acid. If an electron pair from the base is used to attack the acidic proton, then the conjugate base must break off to avoid breaking the octet rule. The arrows used to describe an acid-base reaction are quite simple, since only one bond needs to form and one bond needs to break. We can prove that these events occur at the same time in a concerted manner from the rate equation, which is bimolecular. As we move towards more complicated processes, we need to keep track of which bonds form and break and match the mechanism arrows to the available evidence. As with all of the reactions to be encountered in the organic chemistry sequence, you will need to be able to use the presented clues to work out what is going to happen. Beginning with acid-base chemistry, you should be able to identify straight away which species is the base, which is the acid, and what products are expected to form. Once that is established, we will be able to discuss which side of the equation is more likely to be more stable and therefore favored.